Okay, so hi guys. Today we'll be solving a LeetCode easy problem, but the thing is like we'll not be solving it in a naive way or uh, you know something. Basically, we'll be discussing math solution for this problem. So yeah, just checking like if my screens are fine. Okay. So basically, I think everybody would have heard of this problem majority element. So basically, you are given an array and you need to find that element which appears more than n by 2 times. Uh, this is like the floor value of n by 2 times. So that is the question, and then but the thing is like we can very easily count every number's frequency, and then we can just put a if condition. If that number is greater than n by 2, if that number is appearing greater than n by 2 times, then definitely okay, that's our majority element. But the thing is like why I picked this question is not because this is very simple to come up with, but there is one more approach to solve this problem, which is which is totally maths oriented. And to think about that solution, I think it will totally, like, if you are new to solving problems using maths, or you've not heard of this solution before, this will totally blow your mind. So just uh, I'll explain the problem, and I'll tell you how to come up with that solution. How somebody, if there is a statement in maths we make, how that statement is going to be true, and how using statements we can actually come up with a programming solution for this. Okay, so let me just you might have heard of this principles like pigeonhole principle or inclusion exclusion principle. But the thing is like from very beginning, whenever these principles used to come or somebody used to teach me about these principles, I would never be able to digest it. Basically, it will never come to me like an intuition or something. Okay, but the thing is like we will be using literally maths, probabilities, and expectations to come up with a solution for this problem. Okay guys, so let me start. Let me go to my iPad screen. Okay, so let's say you are given an array. Okay, and we know that there is a majority element in that array. So basically, if you see, there are elements. So let's say this is a majority element. So there are elements which have frequency. There is definitely an element which is having frequency greater than n by 2. Okay, now the thing is, let's say we select one index. Okay, any index I we select. Okay, now what I'll ask you a question, like what is the probability that this index has this element? Okay, so basically what is the probability? So let's call this at p of p of it, that we hit, like we selected this index and we have found the majority element. Okay, so what is the probability? So there are total of n numbers, and we have like greater than n by 2 number of majority elements index. So probability that we selected an index and we landed upon the majority elements is going to be greater than 1 by 2, right? That is greater than 0.5. Now if I tell you like if this is the probability of hit, what is the probability that will not be able to select this index? Okay, so that is nothing but 1 minus p of hit, right? So yes, so this is what you can definitely say, that this is very, high school level maths, nothing complex. Okay, so this is going to be, if this is greater than 0.5, then this thing will be less than 0.5, right? This thing will be less than 0.5. Okay, now in probability, you might have heard this term where if we kind of calculate the probability which is like dependent on previous probabilities, so we kind of multiply that thing, right? So let's say we again do this. We again select one index. Okay, then what is the probability? Then this will be 0.5 less than 0.5 into less than 0.5. Okay, now this will become less than 1 by 2 into 1 by 2. Okay, so this will, how, let's say we do this for like 20 or 30 times. What does this become? Probability that we are going to miss the index is lesser than 2 to the power, let's say we did it 20 times, that is 1 by 2 raised to the power 20 times, right? So this probability, if you see, will come around 0.000 something. So I think this will be like, I don't know how many zeros, but yeah, certainly it will be 0.0001. Now what do you conclude from here, right? So the thing is, if we are able to select a randomly, if we are able to select a random index every time for, let's say, 20 times we do this, what is the probability that we will what is the probability that we are always going to miss, that will never be able to search our majority element? What is the probability that is less than 0.00000 some one? So I think it comes out to be somewhere around 780. Okay, maybe we can calculate that later. So, and what is the probability that we will get our index? That is 99.9999. Now, can we use this math to solve this problem? So this was the whole explanation, that how maths can make things very simple and easy. Now I'll tell you the solution. So basically, what we can do here is, every time we can choose a random index, and then we can check whether this random index is a majority element or not, right? And if we do this for 20 times, we'll definitely get our majority element. Yes. Now let me go to the solution. Okay, it was not very big of an explanation, but I'll just go to my solution. If you see my solution, this is the solution. So basically in this solution, what I have told is that everybody can come up with frequency and count approach to solve this problem. Okay, but what about if I tell you that we randomly choose an index and say that this is our majority element, right? So what is the probability of that? So basically the things that I've explained you just now. Now to do that, it's very important that you have an understanding of random number generators. So basically in C++ we have this high precision clock. So even like if you want to read, you can read about this, but definitely you can, without even reading that, basically you can understand this will every time give you a random index with some, there is some collision principle and all, which will not go in detail, but this is a very high precision random number generator. Okay, now what I have done, I have used this random number generator function, and I am generating a random index I'm generating. Okay, and I'm assuming that I have found I'm assuming that this is my majority element. Now what I'm doing, I'm making the count of this, right? So if the count is greater than 1, then this is our majority element, right? So I think I hope you understand this part, right? So this is how we can definitely code this problem. Now this is a very beautiful thing that, this is nothing that I came up with. It was basically in a class uh, where one of the competitive programmer, like, you might have heard of him, he told me about this, uh, and this totally, it was a mind-blowing moment for me. Ki how, someone can easily uh, you know come up with few high school level maths and do magics like this. Okay, so basically, even I had solved this question before. You can solve this in O of 1 space, right? Basically, the whole question, comes down to this, right? You can count the frequency as well, but that is not O of one space, because you will be utilizing map or something to store the frequencies of every element. But how can you come up with the O of one space? So if you see my solution, that is kind of even not using map or frequency. So basically, what I'm doing is, I know that at last, if I'm getting a majority element, so if you count the whole thing, and for every majority element, if you increase the count, right? So eventually, if there is a majority element, so count will always be greater than 1, right? Greater than or equal to 1, right? So this is how you can, come up with this solution. Now I have one more problem, which is, basically, I thought maybe I was not able to come up with the solution so frequently, so I thought maybe I'll discuss that as well. Okay, so I think the problem was, let me just open my summations. Oh, yes. So there is this problem. Now let me just, okay, let's hit it. Now it's a medium level problem, but it actually teaches you a lot of things, and I'll tell you, 3 ways to solve this problem. So basically, 3 different solutions, 3 different approaches, and 3 different solutions for this. Okay, so basically, you are given array of non-negative integers and an integer k. An array is called spatial if bitwise OR of all of its element is at least k. Okay, that is, if there is an array, or like, any segment which has a or at least k, that is greater than equal to k, then that is a spatial array. Now we have to return the length of the shortest spatial non-empty subarray. Okay, if no subarray exists, then we can return this. Now this question, will be very easy if you know the properties of OR. Okay, now let me go back to the things. So basically, if you OR 2 number, right, basically this will be always greater than or equal to max of a comma b. Okay, now let's say I have something like prefix or something. So if this is like, if I'm ORing every element and storing it as a prefix or something, basically the OR will never it will never unset a bit, or maybe a different way to, it will never turn off a bit. So basically it will never turn off a bit. Its properties are different. So it will either make a 0 to 1, but it can never make a 1 to 0, right? So if there is a 1 in front of 0, then if there is a 1 in front of a 0, then it will make 1. Otherwise it will never turn off a bit. Now this properties can be extremely useful while solving this problem, because this will give you the idea that for any subarray, for any subarray, like basically if I say, let's say this I to j has an or value of some x. Okay, if this has an or value of some x, if I add one more number, okay, the value, this x value will not decrease, because in this x no bits will be ever turned off by addition of a value. Now this statement is very crucial while solving this problem, because this will open up possibilities of thinking about even binary search, thinking about even sliding window, or you can even think about a very I'll say unintuitive solution which I also came up with, uh, like I came up with later after seeing solutions of other people. So that was like some sort of a solution, because you'll see that the new jar will never exceed a 32-bit number. So that was another observation which could actually be used for solving this problem. Now, okay, so you know that for a subarray size of x, if there is an element which is coming in, it will only increase the value, right? Increase or make it like just keep it stagnant, like keep it constant, right? Now the very first thing which came to my mind was to use a sliding window and just solve this problem. But i was I was not able to think how to which technique to use, like whether to use a decreasing technique or an increasing technique, or like even if let's say we choose a technique, how do we slide our windows, right? So that if you're not able to come up with something like that, then of course you cannot. So I'll tell you, like whenever there is a problem of like sliding windows or anything, there is another solution of binary search for sure there, right? So i I will first try to explain the binary search solution. So let's try doing that. Okay, so let's say there is an sub array of size, let's say x. Okay, and what I say, okay, let me think. Actually, just let me see the statement of the question. We need to find shortest subarray. Okay, so let's say there is a sub array of size x, okay, which has a or value, like total or value of k, or like exactly in the, which has at least k value of or. Okay, now can I say ki if there is another sub array of x plus something size, okay, if there is another sub array of x plus something size, then also it will have at least k or, definitely, right? Because adding elements in the array will only increase its value, it will never decrease, right? Increase or equal again. Now if you see this element, if you see this statement, this is the whole basis of binary search, right? So let's say I first, there is some x, so I write f of x is equal to, f of x is what, then x plus something, so like for x greater than something, it will be definitely true. So do you agree that our predicate function will be something like this, and we need to find this smallest
x. So basically this is x, this smallest x, right? Because for x plus something it will always be true, but there is going to be a x, you know, if you consider this x, for which it will be false. Like basically if there has to be a limited size of subarray after which it becomes greater than equal to k, and below this it will never be possible, like it will be always be false, so we'll need more elements to add, right? This is the basis of the binary search solution. So I don't know which solution was binary search. I think this one. Yes. Is it? No, this is not the binary search solution. I think yes, this has more. Yes. So if you see this is the binary search solution. So we assume that our subarray size is x, okay, and then we try finding, you know, for a x subarray size, for a fixed x subarray size, we try to find if there is even one subarray whose value goes over or equal to k. Then we return, you know, then this function is true. Basically this is one of the potential answers, but we need to minimize this answer. That's how binary search works. So basically to come up with a binary search solution for any problem, you need to find, you know, this predicate function. If you're able to come up with some statements like this, then definitely you can, you know, use binary search there to solve the problem. Now let's go. I will tell you another solution for now here also you should come up with like how do we find, you know, that x fixed? Are we going to or every x again and again? No, right? Again that will like for every length, if you every length of x subarray, like if you imagine there are l minus x subarrays for and if you try to because definitely we'll be using the or value only, right? If the to check the our predicate function, we'll be using the or value in fact. So this x is, you know, if the x size or of x is greater than equal to k, then it's true for x greater than x as well, like, right? Otherwise for less than x it's always false, right? So this will need to check. Now let me tell you about a different solution for sliding window thing. Okay, now to come up with sliding window, it's the same statement ki if we have, you know, a window, if we have a window of size a window which is, you know, greater than equal to k, whose or value is greater than equal to k, then I can say that any window with a larger size, like any window with a larger size, like let me use another color or something. So any window with a larger size can also be said to have a or value greater than equal to k, definitely. So here comes the optimization using two pointer. So basically our binary search problem was giving a time complexity of n log n. Here we can use two pointers to maintain, you know, the window length. The window length we can maintain it using two pointers as well, right? So how will we do that? So we can have a left pointer and we can have a right pointer at the start of our array, and we'll kind of keep if we, you know, okay, if we found a window, right? If we ever found while expanding or whatever we'll do, let's not worry about that. If we ever found a window whose OR value is greater than equal to k, right? This can be our potential answer, right? So at that time, let's say L was, the left pointer was at L and right pointer was R, right? So we'll need to take the minimum of all the lengths. And what will this length will be? It will be R minus L plus 1, okay? Let me just show you the solution. So basically, I just want to give you, idea how you can, you can directly go to the statement, and then once you have made the statement, you can quickly write the solution. Okay. So let me, I think this is the sliding window. Yes. So this is the sliding window. So here, as you can see, I have taken 2 points, left pointer and right pointer, okay, which is initially at the start of the array that we are given, okay. Now, what I do here is, as soon as I have found a window whose value is greater than or equal to k, I know that this can be my answer. Right, so this length can be my answer, right? And I have updated my answer as well. Now the thing is, how do you, yes, now I'll discuss about how do you actually move your left pointer, on what condition, because this is OR value, right? This is OR value. So if I tell you A or B is equal to k, right? So how do you kind of, without losing this count of OR, how do you move your left pointer so that you don't have to recalculate again, right? So I don't think like if you guys understood, but let me just try again. So let's say LR, we are using 2 pointers, right? So how do we do 2 pointers? We have found a window of length k, sorry, not length k, whose OR value is greater than k, right? Now the thing is, we'll need to move our left pointer, right? So how do we move our left pointer? So basically we need to, like, if this was sum, right? If let's say this was just sum, right? Then the value at this pointer, so A of L, I could have subtracted it, and then I could have moved it, because we have to maintain only this window's sum, right? We don't have to maintain, or we have to maintain only this window sum, and we don't need to count every window again and again. Otherwise, what is the use of using 2 pointer and trying to optimize our code? Okay. So how can you think of in terms of OR? How can you think of the same thing, right? So I'll tell you a very cool way to think about this. Let's say your numbers were, so just imagine the bit of this, right? So just imagine the bitwise representation of those numbers. So we don't need to actually calculate the numbers. So these are the numbers which are in my window right now. Okay, these are the bit representation of those numbers which are in my window. Okay. Now, if you see this number, right, this is my A of L, right, and this is my A of R. Okay. Now, if you see the bits which were set here, right, these bits we need to remove, if we think in terms of only bits, we just need to remove these bits, right? Right, if you remove these bits, then we can say ki, okay, now we can move our L. Now, but the thing is that what will be our new value now, right? We cannot go to every number and check, or we cannot even OR every number again, right? So again the property of OR comes in, right? So let's say if this number was a of L plus 1, a of L plus 2, something like that, okay? We can maintain an array of 32 like 32 size, and we can just check key, and what we'll store in that array of 32 size is like every bit. So at every bit we'll store the count. We store the count at 0, then count at 1th bit. We can store the count of that, and then we can just check if this value is greater than 0, then definitely the new OR value, right? The new OR value is equal to in the new OR value bitwise. If we represent the new OR value in terms of bitwise, then this bit will be set if that count of bit is greater than 0, right? So here it will be 1, here also it's greater than 0, so it will be 1, here it will be 1, and here it will be 1, right? So do you see like how much the property of OR is being used here? Because we don't want to OR everything again. We don't want to OR everything again. This will again increase the time complexity. Instead, we can just see if there is even one bit set anywhere at that bit, then this bit will be set in the cumulative OR of this, right? So this was also one of the property of OR that was used. So if you see how I have moved my left pointer, is I have checked कि bits I is greater than 0, then this is the OR value. I have again set it to 0. This is the new OR value actually, and I have given it when you left shift by I, that is like 2 to the power I, we kind of multiply that, right? And here I have updated the bits count, right? So basically whenever I'm getting a right number, I'll have to update those bit counts at every ith bit. This is the nums, right? And with 1, so that is checking whether that ith bit is set or not, and if it's set, then bits I plus. It's exactly as simple as that. So I think this has been a very long video. Anyways, you can actually ask me if you guys have not understood anything, or if there is any doubt or anything. Thank you.